Okay, hello everybody. My name is Nick Barrett. I work for the French Atomic Energy Authority, the CEA, based in Saclay near Paris. And today I'm going to present some of the work we've been doing on ferroelectric structures which we've observed above the Curie temperature at the surface of barium titanate. I'd like to thank Michael Merkel and the Focus team for asking me to do this presentation, and I do hope that next year in 2021 we'll be able to meet up and discuss in more detail. Okay, ferroelectricity. Material is ferroelectric if it has a spontaneous net dipole moment which can be reversed under application of an electric field. Now it's called ferroelectricity, but it doesn't have anything to do with iron. It's called ferroelectricity by analogy with ferromagnetism. The electrical polarization displays a hysteretic behavior with the electric field. So there's a coercive field, there's a saturation polarization, and very importantly, going back to zero electric field, there's a remnant polarization. And this makes it particularly interesting for all sorts of applications in microelectronics. This year, by the way, is the 100th anniversary of the discovery of ferroelectricity. It was discovered by Joseph Valasek, who presented his work in the 1920 American Physical Society meeting. Now, barium titanate has an AbO3 perovskite, is probably the prototypical ferroelectric. The Curie temperature is 120 degrees C, so 393 Kelvin. Below this temperature there are ferroelectric phases. The room temperature phase is tetragonal, and in this tetragonal phase, instead of having a centrosymmetric structure, the titanium cation is off-centered with respect to the oxygen octahedron, and this gives rise in the unit cell to a net dipole moment, and on a macroscopic scale to a net polarization. When the temperature goes above the Curie temperature, above 393 K, there is a structural transition to a cubic structure, and the cubic structure is centrosymmetric, there's no titanium off-centering, and it is non-polar. What we'd like to do is look at ferroelectric contrast using PEEM. Now, PEEM, as you know, is based on photoemission. Here's a typical spectrum. There is the photoemission threshold with the secondary electron peak. You have the distinct core levels at higher energy, and near to the Fermi level you have the valence band. But for our purposes we will concentrate on the photoemission threshold, because this gives a direct measure of the sample work function, or in the case of barium titanate, of the surface potential. Now, ferroelectrics order, in order to minimize their energy, into domains which have homogeneous polarization. This is shown here for in the case of a thin film, and you can see that it is made up of alternating downward pointing and upward pointing domains. The domain polarization gives rise at the surface to a net polarization charge, and in fact a surface dipole, which modulates the surface potential. And the modulation of the surface potential, if you do a measurement in PEEM, is reflected directly in the position of the photoemission threshold. One example of this is shown here, where we see two images of the same area in the sample. The broad vertical stripes are domains. There's some tweedy-like structure in between. And what we can see is, going from 3 electron volts to 3.5 electron volts, that there is contrast inversion between the two types of broad vertical domains. And this is a direct signature of distinct surface potential values, and therefore we can from an analysis of the image contrast, we can deduce what is the polarization at the surface of a given material. Above the Curie temperature, then, we do not expect any polarity. However, there is a considerable body now of experimental evidence which suggests that even in the paraelectric phase there are polar structures. Here's one example. A crystal barium titanate is subjected to an AC voltage. This makes the crystal vibrate. There's a piezo response which is recorded. And here we have, as a function of temperature, we have the frequency spectra. And what you can see is that above the Curie temperature, from this point onwards, there are still very distinct and sharp resonances, which are the signature of polar domains or polar areas within the material. So these resonances exist up to 600 K, and they're thought to be due to ferroelectric precursors which form already in the high temperature, high symmetry paraelectric phase. Our sample, we've checked first that it's well-behaved barium titanate by looking at the phase transition using Raman spectroscopy, and here we can see that the characteristic modes associated with the tetragonal structure disappear at the Curie temperature, leaving only the modes associated with the cubic structure. Similarly, X-ray diffraction. Below the Curie temperature, we have the two characteristic lattice parameter values corresponding to C and to A. At the Curie temperature, there's a sharp, mainly first-order transition to the cubic structure. So that in the bulk, our system is well behaved, and there is the structural transition from tetragonal to the cubic structure. But at the surface, this is not what happens. Here we have the PEEM images, and we have a series of PEEM images as a function of the electron kinetic energy. We can then, using an automated fit procedure, we can then look at the photoemission spectrum at each and every one of the pixels in our field of view. Extracting the intensity from a given pixel coordinate will give us a single threshold spectrum, and we then fit the ensemble of these threshold spectra using an error function. This means that in a given field of view there is something like 300,000 spectra to be analyzed, and once we've done that, we can then reconstruct here not an image but a map of the photoemission threshold. And as you can see, there are three basic levels of intensity: bright yellow, dark yellow, and brown, and these correspond to three distinct surface potential values, reflecting the three possible polarization orientations at the surface of barium titanate: out of plane pointing upwards, out of plane pointing inwards, and in plane. So we have a true surface potential map reflecting the ferroelectric polarization. And this experiment, and here's the main result of the work, this experiment we've done for a series of temperatures. First at room temperature, that's what I showed you. Then at about 100 degrees C, so still below the Curie temperature. Then we passed the Curie temperature, we carried out the same experiment at 450 K, and then finally 550 K. Now the first thing to remark is that the overall structure due to the ferroelectric domains persists and is conserved up to 550 K. So this is direct evidence that although in the bulk there has been a phase transition to the symmetric cubic structure, at the surface polarity is still existing up to something like 150 degrees above the Curie temperature. The second thing to notice is that our Tweedy-like structure has undergone contrast inversion with respect to the surrounding domains. And this has happened below the Curie temperature. The third remark is that the domains themselves, the broad vertical domains shown here and here also undergo a contrast inversion, but this time it is all happening above the Curie temperature. And this contrast inversion, as I said before, is the signature of a change in the surface potential, which we can link to the direction of the ferroelectric polarization. So what is happening here is a switch of polarity, which is the true signature of ferroelectricity. In other words, at the surface region, or the very near surface region, remains ferroelectric above the Curie temperature. And that's about all I wanted to say today. If you want more details on this, then please look into this article by Claire Mathieu et al. In Scientific Reports in 2018. Don't hesitate to contact us with comments or criticisms, and I hope that we will all be able to meet up, as I said, next year in the Focus PEEM workshop. So thank you for listening.